and we effectively pose the problem as a convex optimization problem where we are given a matrix X, and the goal is to decompose that matrix X as the sum of a low rank matrix and a sparse matrix. So again, the assumption is that this matrix is low rank, and this matrix is just a few sparse corruptions. And we minimize these with respect to the low rank part and with respect to the sparse part. We had a theorem that effectively said, in words, something along the following lines, which is that if the rank of L is small, and the percentage of corrupted entries is also small, okay, then, and L is mu incoherent, the typical requirements, then the optimal solution is equal to the true, and the optimal solution for E is equal to the true. Okay? Where this is, maybe I should have said that the X is equal to L naught plus E. That's more or less what we spoke about. The other aspect that we spoke about was how we solve it was by defining a Lagrangian. Which is just the objective function plus lambda times E1 plus the lambda times the constraint, but we utilize an augmented Lagrangian approach where we also penalize the constraint squared. And we demonstrated that the following algorithm solves the following optimization problem. So we start with E0 equals sum lambda 0 and is equal to 0. The beta is a parameter of the algorithm that needs to be non-negative. And we follow the following iterations. We first update the low rank part, and the way we update the low rank part is by applying the shrinkage thresholding operator to the SVD of the true data minus the outliers, and corrected by the matrix of Lagrange multipliers. Then we update the outliers, and we update the outliers by taking the data matrix, subtracting the low rank part, again adding the correction term due to the Lagrange multiplier, and then we do shrinkage thresholding with parameter, I think it was lambda over beta, yeah. Maybe I'll write 1 over beta here. Same. And then we update the Lagrange multiplier, and that's always easy, is equal to the previous, plus beta times the constraint, so it should be x minus lk plus 1 minus ek plus 1. And that was the algorithm. I probably here should be lk plus 1 because I already have it. Okay. So I repeat again, I ended up explaining that the algorithm is just super intuitive. Again, the goal is, given a data matrix, decompose it into a low rank and a sparse part. And the algorithm just iterates between, effectively, you can always understand this as make a low rank approximation of the data minus the outliers. And this is make a sparse approximation of the data minus the low rank part. And in that way, you get an L that is low rank, and you get an E that is sparse. Okay. So what I wanted to show here is an application of the algorithm to phase images.
question?
Yes?
So this is guaranteed to converge?
Yes.
Setting beta how?
For any beta that is larger than 0.
Even very large beta?
Yes. So the analysis of convergence is a little bit more involved than usual. So the standard ADMM algorithm, this is an augmented Lagrangian style algorithm. And effectively, the way to understand it is that you've got the primal variables that are L and E, and the lambda, which is the dual variable. There is an algorithm called the augmented Lagrangian method that is guaranteed to converge. And the ideal method should operate in the following way. You should do an update of the primal variables, so finding the optimal primal variables, and then do an update of the Lagrange multipliers. Okay? This algorithm is what in principle is called approximate augmented Lagrangian. The reason being the following. Theoretically, in the exact augmented Lagrangian method, as I just said, you should update the primal variables by finding the optimum value for them, which means minimize this entire thing with respect to both L and E simultaneously, assuming that lambda is fixed at the current iteration. What we are doing here is slightly different. We are actually fixing lambda and E before we solve for L. And the reason we do that is because we get a closed form solution when we do that. If I wanted to minimize jointly over lambda and E here, I wouldn't get a closed form solution because you can immediately see, in fact, that L depends on E and E depends on L. So the equations between L and E are coupled if I wanted to do the exact algorithm. So the reason why the proof of convergence is also non-trivial is because effectively this is a sort of a primal dual method. Alternating minimization is okay. You know, if I didn't have the lambda part, right, this would be okay because you find the optimum value for L given E, you find the optimum value for E given L. And so at each step you're guaranteed to go down. The problem is that when you have the extra step of gradient ascent on the Lagrangian, now you could potentially go up. So in order to prove the convergence of this algorithm, what really happens is that I go down, I go down, I go up. And in order to prove convergence, you need to demonstrate effectively that how much you go up here is less than how much you went down here, so that with the 3 steps you still go down. The analysis of these type of algorithms has been well studied, and effectively this is what's known as augmented alternating direction method of multipliers, because you're alternating the 2 direction here. And this is called the 2-block method because I am alternating over 2. A more general version would be, suppose that I divide all of the primal variables in multiple blocks, more than 2. And in that case, I would be doing each one of the updates of each block and then the Lagrange multiplier at the end. So it is true that the analysis of convergence is complicated, and actually all of the original results for the convergence of ADMM were just for the 2-block case. And the multi-block case was only recently studied. I think there were a few papers starting in 2010. But at this point, the multi-block case, you can also prove convergence, but you actually have to do a little tiny modifications to the way the updates are done. And over there, I think the choice of beta starts to matter. But I think for the 2-block case, this is fine, and I'm not covering the detail. Again, this is not an optimization class. I use optimization as a way of deriving the algorithms. But all of the technical details pertaining to optimization and convergence, really you should take a class on convex optimization. And I think the Applied Math department has a couple of classes on those. Okay. So let me now show you some examples of how this algorithm can be used and what would be applications where this is relevant. So coming back to the example of phases, I've said a couple of times that in the case of phase images of individuals under varying lighting conditions, you can approximate them well by a 9-dimensional subspace. Or it really depends on computer vision models of how light gets reflected into surfaces. And for very simple computer vision models, you can show it's rank 3. For more sophisticated models, you can show it's rank 9. But the assumptions under which a subspace is a good model for phases under varying illumination is that the surface being illuminated satisfies some property of light reflectance that was studied by a French scientist called Lambert. And so that's why they end up being called Lambertian surfaces. So a key assumption is therefore that you have a Lambertian surface. In fact, if you go to computer vision literature, the theory is always developed for a sphere. So the object is a spherical object. And then that's so that it's always concave, and so the normal to the surface dot product with the normal of the lighting directions, you get a unique thing. So what happens is that when you apply these to real images, first of all, the assumption that you have a concave surface is not true, right? You have the nose, that's the out, and so on. And then the way in which our skin reflects the light is also doesn't satisfy exactly the assumptions of a Lambertian surface. By the way, what does it mean in practice, a Lambertian surface? What is the very intuitive explanation? It really means that the brightness at a point on the surface, as projected into the image, should be independent of the viewpoint. So if the observer starts to move, the image doesn't change, the value of the brightness. But obviously there are all of these regions, or these points in the image. So particularly you can see in the nose is one typical example, where you get this bright point, which is sort of the reflection of the light source into the object. And as you move, the location of that bright spot is also going to change. Okay. The second thing that affects images in this particular case is that because the object is not concave, there are shadows that are caused, right? Because if the light is coming in this direction, the nose will produce a shadow on the other side. So all of these are sort of violations from the Lambertian model. And therefore, this is exactly a case where, going back to the effect, so what we're assuming here is that each column of X is an image of a different phase, and the images have been vectorized. And in the ideal case, the collection of all images from multiple individuals will form a low-rank matrix. Ideally, say, of rank 3 or rank 9, depending on the illumination model. But what's going to happen is that every location that corresponds to locations in the surface, they're typically called specular point or specularities, which are those shiny points where they're going to move as I change the viewpoint. So all of these locations are deviations from the subspace. And all of the locations of the shadows are going to be deviations from the subspace. So the idea then is that I'm going to decompose a phased image that contains specularities and contains shadows into a low-rank part. And so the low-rank part would be how would the phase would look like if the phase was Lambertian. Plus an extra image that is supposed to be sparse because it should be non-zero only at the locations of the specular point and at the locations of the shadows. So that's exactly what's being observed here. So at the top, what you get is the input images to the algorithm. And in this particular case, I'm showing 4 examples, but I forget. Probably there were 30 or 60, I forget, 64. So the algorithm took a matrix, in this particular case, that is number of pixels by 64, and applied the algorithm to that. And so what you see in here is the low rank component. So this is now taking every column of L, once it's been computed by the algorithm, and reshaping it back so that it looks like a face, so that it looks like an image. And at the bottom, what you see here is the sparse components. And they're plotted so that if the matrix has a 0, that should be black, and if the matrix is non-zero, it should be brighter. As you can see here, it says this is via the exact augmented Lagrangian algorithm. So the exact augmented Lagrangian, I did not present it in class, but as you asked me the question about convergence, I said, what if I am able to jointly update L and E at the same time? That is what the exact augmented Lagrangian method is. And so these are the results that you get. And these ones here at the bottom are with the inexact, which is the ADMM method, which is the one that is described. So the first observation I want to make is that look at the differences. It's very hard. In fact, the differences between the exact and inexact is really very, very minor. It's just numerical precision at the end of the day. But the inexact algorithm is significantly faster because we can compute each one of the two in closed form. Okay? So to be able to do the exact, just to tell you a little bit, you don't get a closed form solution. So you actually have to run many, many iterations to compute the optimal L and E for that given lambda. Okay. So the first point is to just sort of try to convince you that in practice it doesn't make much of a difference, and this algorithm is way faster, so that's why in practice people use this one. But now let's start to look at what happens. And maybe I'll just illustrate it with the one in the top so that you can see the three at the same time. So what you can see is immediately, right, what is the sparse part? Look at this part. What is that? That's exactly the shadow on that side of the nose, right? Then you get some of the bright spots that typically show up in the skin, and you look at the eyes, because they have a lot more water, plus the shadows, plus the specularities, plus regions of the face that have very different reflection properties. All of that gets lumped into the sparse components. And that's what you should expect. And in fact, it's very funny. If you look at the eyes of the person, right? I mean, this looks like a regular picture of a person, right? You can almost not tell that it's been processed. But if you pay with a lot of attention, right, at the center, you don't see the typical bright spot. Okay? So there is very minor variation. But anyhow, and now in comparing, for example, this image that has a lot of shadows and you can not see the person very well, here you can see the person in general much better. Okay? So it's a way, in a sense, to automatically, even though this came out as just low-rank PCA, when you start thinking about applications, this can be very useful for a variety of things. So in particular, this gives you an automatic way to remove shadows and remove specularities from these. I don't think it's been tried with the typical red dot effect, but presumably if this was applied to color images, it's sort of the same type of effect to be removed. In fact, I didn't mention it here, but you can potentially do examples where all you do is that you take face images and you just put some text on top, okay, of a different color. And now you corrupt all of the images by putting text. And now, when is this going to work? If you put the same text on every image in the same location, what should happen? Will it work or will it not?
I guess I would hope that would come out as the sparse part, text.
Okay, I did not write the theorem, but what does the theorem say? What are the properties of the corrupted entries? Huh? They need to be uniformly at random. Okay? So, if I modify a picture by putting text in the same location in every single image, What that means is that I will be corrupting the matrix X. I will be corrupting the same row of X, because each row of X corresponds to a different pixel. Right? So I'll be corrupting the same row of X identically in the same way. So every single, the entire row of it is corrupted. Okay? So this algorithm would actually work, you would think, right? It's a little bit counterintuitive. You would think, well, if it is always in the same location and it's always the same text, that should be an easier problem. And it is easier for us humans because we will detect it's always the same, it is the same text. But actually, once you remove it, what do you replace it by? Right? You will need to run some extra computer vision algorithm that reasons about the fact that nearby statistics of the pixels should be the same, so I can have a way of doing in-painting, which is sort of the computer vision task associated with it. But from the pure machine learning perspective, what the theorem says, the theorem wants the missing entries to be uniformly at random. So it would work much better, and in fact, without knowing any computer vision, it would be able to correct all of those corruptions if the text appear in different locations in every image. Because the whole point, in fact, the reason it's being able to correct the value, why did it was able to handle that shadow in here? The main reason it was able to handle the shadow in there is because there is another image where that region is not in shadow. Because it is exploiting the low rank properties of L across all of the examples. Right? So if a pixel is corrupted in all of the images, there is no statistics, there is no examples under the right elimination condition from which I can recover. So that's exactly with this uniformly at random thing is showing up in this particular application, that you want to have examples of the intensity of that pixel that are not corrupted so that you can recover. Okay. All right. Okay, so I'd like to move on now to the next type of corruption. So the first kind of corruption was some entries of the data are missing. The second kind of corruption was some entries of the matrix are corrupted. The third kind of corruption is what we call outliers, which in picture means I've got the data is in the subspace, but then I've got some points that are very far from the subspace. And that's what we call outliers. So here, if I relate it to the example we just looked at, right? This is an example where one entire column of the matrix has been corrupted and replaced by, say, completely random values. So relative to the previous type of corruption, we can no longer expect to recover that column, right? In fact, I just explained that if one entire row is corrupted, there is no way I can fix it. If one entire column is corrupted, there is no way I can fix it. So the problem here is now of a slightly different nature. I don't want to recover the exact matrix. What I want to do is to differentiate between the ones that are not corrupted versus the ones that are corrupted. So this is what I would call an outlier detection, to distinguish just between the two kinds of data points. Okay? Now, why is this relevant? I would like to illustrate that with the simplest case, which is the case you're trying to fit a line to data. And so if all of the points are right here, you're going to do your PCA fit, you're going to get the first principal component, and you're going to get your line very well. But if you happen to have one point, let's say here, and another point, let's say here, okay? And actually, let me even exaggerate, suppose you know that that point was much farther and that point is much farther. I can guarantee you that it's more likely that you're going to get a line that fits the data. If you use those extra two outliers, you're probably going to fit a line that passes through the outliers. So, in fact, even one outlier that is very far from the subspace can completely corrupt your estimate. So the whole point is, can I detect which ones are outliers, ideally eliminate them from the data set, and then just feed the subspace to the inliers. Okay. So these are going to be the inliers, and this is an outlier. So this is a problem that has been studied for a very long time, and if you look at the literature and statistics in the 1960s and 70s and so forth, there were many robust PCA style methods that were applied to solve this problem. And I will be discussing some of them later, not today. Because I actually want to just continue sort of with the same philosophy that we've been proceeding so far, which is sort of the philosophy of the last 10 years of machine learning, which is all based on convex optimization, based on nuclear norm and L21 norm. Okay. So I would like to say, well, could we do something like what we just did? Could we somehow take the data and decompose it as the sum of the perfect data and the sum of the plus the outliers? And so in order for that to be the case, this is the right decomposition, which is slightly different from what we've been discussing so far. So if this is X, okay, suppose without loss of generality, just for the sake of analysis, that I can split that matrix into the part that corresponds to the inliers and the part that corresponds to the outliers. Okay? That's how the matrix looks like. So, clearly, a valid decomposition of that matrix is as follows. To put all of the inliers here, and to fill in all of that with zeros, plus, now I'll do the opposites. Now it's 0 here, and here I've got the outliers. Right. And so this is going to be, again as before, X is equal to L plus E. Okay? So now, because this piece of the matrix is the matrix of inliers, these are all the points that are supposed to be perfectly in the subspace, right? So, if I had access only to that piece of the matrix, which I don't, I would know that that matrix would be low rank. Right? The rank of that part would be equal to the dimension of the subspace. What happens if I take that matrix of inliers and I augment it with a bunch of zeros? What happens to the rank? Huh? Stays the same. So what I can say is that the rank of L is equal to D. There is no change. Now let's analyze the second matrix. What property does it have? Before, when I was corrupting some of the entries, my assumption was that the percentage of entries of the total matrix that are corrupted was small. Now, this is no longer the case because since an entire column of the matrix is being corrupted, right? That particular column will not be sparse in any ways. It could be dense. So I can no longer say that the matrix E will be sparse, although it will be to a certain extent, right? Because all of these columns will be identically equal to 0. So the overall matrix might still be perhaps sparse. But just saying that it's sparse in terms of the entries is probably not a good metric. It's probably not a good way to describe it. So what is a better way to describe it? A better way to describe it is to actually say that the percentage of columns of the matrix that are non-zero is small. Because effectively what I'm saying is the percentage of outliers hopefully should be small. So this second matrix should be what I'm going to call now column sparse. Okay? And now the question is, how do I measure the column sparseness? I'm going to measure it with the so-called 0, 2 norm of the matrix, which is the sum, and I'm going to put a 1. Well, the sum, and I'm going to put a 1 every time the column J is different from 0. In fact, let me not even write it with the 0, 2 norm yet. Let me just write the number of columns, the number of non-zero columns of E. What is the number of non-zero columns of E? Is equal to that, right? J equals 1 to N. That's what it is. I just go column by column, check if it is non-zero. If it is non-zero, I count it with a 1. And then just sum from 1 to the number of columns. Trivial, right? Okay, what I'm going to do is to actually modify this slightly to say that this is the same thing as saying that J equals 1 to N. I'm going to put a 1 each time the norm of Ej. And I'm going to use any norm for now. The norm of Ej is non-zero. Okay? Because if the vector is non-zero, the norm of it is non-zero. But what this does, in fact, and that's what's interesting, is that it converts the matrix. Originally I had E, and that E was a bunch of zeros and a bunch of outliers. Okay, I've converted that into a vector right now that contains the norms of that matrix. I take every column and I compute the norm. So this is norm 1, sorry, the norm of the first column, the norm of the second column, okay, the Q norm, and here it will be the Q norm of the nth column. Right? Is that clear? That I took a matrix that originally was D by N, and I'm converting it into a vector of dimension 1 by N that just contains the norm of every column. Okay? So all I'm claiming now is that if this matrix is column sparse, that's the same thing as saying that this vector is sparse, right? Because effectively, all of these are going to be zeros right now. And in fact, the number of non-zero columns of that matrix E is exactly equal to the number of non-zero entries of this vector of norms. So that's why now I'm going to call effectively that this is the 0, Q norm, which is the number of non-zero entries of, how do I call this vector? Let me call it V. V. Is that clear? All right, so the number of non-zero columns of E is the same thing as the number of non-zero entries of this vector V. And how do I obtain V? Just compute the norm of every column, and any norm is as good as any other norm. Okay. But as we've been doing over and over, we start with number of non-zero entries, and then we relax it to the L1 norm. We start with the L0, and we replace it by L1. Okay. So I'm going to use this notation right now, which is, what if I, so that's what I mean, that's what I put a 0 there, because it's 0 in one dimension. Actually, am I doing it right? I think I should be Q, 0. Because the notation is trying to symbolize the fact that I take the Q norm in this direction and I take the 0 norm in this direction, because I'm counting the number of non-zeros in this direction. So that's why it goes in that order. Okay? So effectively, this is a way of counting the number of non-zero columns, but if I put 0, q, the same analysis holds true, right? It'll be counting the number of non-zero rows. Okay. So what we're going to do is to relax this, and now we're going to put q, 1. And what does the 1 mean right now? When I had a vector, I was counting the number of non-zero entries, and I replaced it by the sum of the absolute values. Right? So I'm going to replace then, I want the sum of the absolute values of V. That's what it is. Right? That's what the L1 norm is. But what is Vj? What is the jth entry? Right here, Vj is nothing but the Q norm of the jth column of E. So this is, in fact, the sum of the norms of the columns. Okay, so I have this notation right now that says that given a matrix E, the Q, 1 norm is just the sum of the Q norms of the columns. And it is motivated as being a convex surrogate for the number of non-zero columns of the matrix, which is a non-convex function of the matrix. Interestingly, so one particular example would be, what if I choose Q is equal to 1? In that particular case, I get this thing, 1, 1. And what this thing will be, well, what is the L1 norm of the jth column of the matrix? It's the sum of the absolute values of, right? So I'm going to get sum over j equals 1 to n. But now I'm going to get the sum over I equals 1 to b of, and now this is going to be eij, right? Correct? Ah, but that was what we were calling the 1 norm all the time, right? So what in fact, what this tells you is the following. I started at the top right by saying, sure, that matrix E is sparse, so why don't I just use the L1 norm for that matrix? And then I went into the argument of saying, wait a minute, but sparse is not quite right because I really want all of the first so many columns to be 0. And then all of the last one are going to be non-zero. So it has an extra structure on top of being sparse. So that's why we went through all of these calculations. But then I said, oh, there is a family of possible convex surrogates for that number of non-zero columns. And each value of Q will give me a different convex surrogate. And if I pick Q equals 1, which seems to be one particular case, I'll get back the L1 norm. So I hope that this conveys the idea that I have the choice of what Q to pick, and that choosing Q equals 1 may not be the best of the ideas, because if I do so, I'll go back to the problem I just discussed with the L1 norm. And that was very good for corrupted entries, but it may not be good enough for capturing the columns. So that is why in practice, what is heavily used instead is the so-called 2, 1 norm. So now we choose Q equals 2, which is the sum j equals 1 to n of ej2, and this is equal to the sum j equals 1 to n sum, well, what is the 2 norm? That is typically the sum of the squares of entries, and then I take the square root. I equals 1 to 2. That's what it is. All right? So, as a consequence, this is what we're going to try to do. We're going to try to minimize the rank of L plus the number of columns of E that are different from 0, subject with respect to L and E, such that X is equal to L plus E. And that's the ideal problem. Find, of course I need to put a lambda, so let me add that over there. So given the matrix X, decompose it as the sum of a matrix L that is low rank, and another one that has a lot of non-zero, the number of non-zero columns is small. But instead of doing that, we're going to do a convex surrogate, which is going to minimize the nuclear norm plus lambda times E2, such that X is equal to L plus E. Okay, so I hope the explanation that I gave over there motivates where this problem is coming from and why it might be a good idea to look at it. Now, that being said, if I go back to the picture that this is inliers and this is outliers, and we're trying to decompose it as inliers 0 plus 0 times outliers. I hope you appreciate the fact that the problem looks like really impossible, right? It's like given any matrix, right? This decomposition is actually quite weak. It's like, you know, given any matrix, just partition it in two parts, you can always decompose it as the first part, 0 plus the 0, the second part. Right? This decomposition is fairly trivial, it's applicable to any matrix. So the fact that I impose the second regularization that effectively says I want many of the columns of these to be 0, right? If I just gave you a random matrix and you try to do this decomposition and you only penalize the second term, what would happen is that the E that you get will be 0 and everything will be assigned to this matrix. So the only thing that saves you and that says there is some hope that this might work is the fact that you want this matrix to be low rank. Okay. Because if you do the split in the wrong way and you keep some outliers, the rank of this matrix is going to increase. Okay. So again, I insist, the problem looks a little bit impossible. The decomposition is sort of fairly trivial and generic and applicable to any matrix. So the main thing that you hope saves you is that the fact that it's low rank. Okay. Now, as before, we would expect that in some cases this would work and in some cases it would fail. And if you remember, what were the conditions for matrix completion to work? What were the conditions for matrix completion to work? Okay, they're the basic ones. It needs to be sufficiently low rank, it needs to be sufficiently sparse. Or in the case of matrix completion, it was the low rank part needs to be sufficiently low rank and the percentage of missing entries needs to be sufficiently small. For the PCA with outliers, with outlying entries, it was the matrix L needs to be sufficiently low rank, the corruption needs to be sufficiently small. But there was a third condition. What was that third condition? The incoherence, right? The low rank matrix should not be sparse, because otherwise I'll just confuse them. Okay. So what we need here is exactly what is that extra condition. And before it was fairly clear. I want the low rank matrix and I looked at the SVD and I didn't want that SVD to be sparse. Okay? But now the situation is slightly different because we have this column sparse idea as opposed to this sparse idea. So let me introduce the exact definition of incoherence in this case. So definition. A rank D matrix L equals U sigma B transpose. This is again a compact SB. Is okay. So what properties do we want in L? We want it to have, in this particular case, 1 minus gamma times n non-zero columns. Okay. So what we're going to do is that we're going to take matrices L that are not just low rank, which was the generic case before, but now we need matrices L that are low rank, but have a bunch of zeros after. So in this picture, in fact, the idea is that this is n is the total number of columns. So I'm going to say that gamma n are inliers, and 1 minus gamma n are outliers. Or maybe it's the other way around. Okay, it's the other way around. So this is 1 minus gamma, and this is gamma. Okay. So gamma is the percentage of outliers. Okay. So I assume that I have a matrix that is low rank, and it has gamma times n columns that are equal to 0. So a rank matrix with those many non-zero columns is nu incoherent if the maximum value of Vj is less than or equal to mu b over 1 minus gamma n. Where Vj is equal to the jth row of Vj. Okay, what does this mean, and how does this compare to the previous definition of incoherence that we had? So a few observations that are important to be made. Before, we were allowing these sparse corruptions of the entries of E. Okay? So the entries could be anywhere, both in terms of rows and columns. So before, we had conditions for incoherence both for the U matrix as well as for the B matrix. Remember? The rows of U needed to be have small enough norm, the rows of V. First observation is this condition only involves V. And why it makes sense that it should be so is because now we are only concerned about columns of L. So we have nothing with the rows. So all what we care about is really the column space of L. And the column space of L is defined by the, sorry, what matters is really just the V matrix for that. The second modification is if you remember, and I'm going to put it between parentheses here, what was the condition before? The condition before had been that the maximum of this without the square was less than or equal to nu times the square root of d divided by n. That was the condition before, right? So what has changed? Okay. If I didn't have the square here, I would immediately get the square root over there. So this, in fact, is the same thing. But what's happened is that the denominator has been replaced. Instead of having n, I have now 1 minus gamma times n. That makes sense because this is just the number of non-zero. The number of non-zero columns. And so let me actually do the derivation and remind you how we derive this. I've got the B matrix there. Okay. And the idea now is that we have derived this by saying when is this matrix dense? And we had said that it would be dense if it had 1, 1, 1, 1, 1 in every possible row. Okay? And we had said that, sorry, let me see, what am I doing here? So this is N and this is D, right? So what did we say? That because this matrix needed to have orthogonal columns, if our column was completely dense, where all the entries were equal, then the reality is that each value here should be equal to 1 over square root of n, right? So that the sum of the square of the entries, right, would be equal to 1, right? Because the norm of each column needs to be 1. So each entry should have been 1 over square root of n. Then, when I compute the norm of the row right now, I need to sum d times. So that's how I get sum of the squares. So I get, okay, so I get sum of 1 over square root of n squared, and I do that d times. So that's how I get, I sum that from 1 to d. So that's how I get d over n. Okay? And then I go ahead and take the square root in order to get the norm. So the square root of d over n was exactly that calculation. Remember now? I did this maybe a week or two ago. Okay. So what's going to happen now? What's the key difference between my previous calculation and the calculation right now? The key difference is that because the L matrix is supposed to have so many zeros in there, correspondingly, what this means is that I am constraining it so that one entire block of it is the zero matrix. So as a consequence, all of the entries being equal to each other and sum of the squares being equal to 1 is no longer over n, but only over 1 minus gamma times n. So that's how this n ends up being replaced by n times 1 minus gamma. And that's why here I got that in the denominator. Okay? So d over n gets replaced by d over n times 1 minus gamma. And I have the square root, but if I do the square here, I get the square there, and the square root is no longer over there. So that's how I get this. So the only difference is that whether I use nu or nu squared, but that is just a matter of definition based on a constant. So just to make them equivalent, the nu of one is the nu square of the other or something like that. And that is because the papers were done by different people and they introduced different notation, and that's sort of what becomes the standard. So they define it with the squares and the previous guy defined it without the square. Okay? But I hope that you get to the idea that the definition and the motivation behind it is identically the same as before. And the main modification is that we only care about columns, so we only care about V. And then a fraction of the entries are zeros, so that's why we need to have this correction factor. Okay? The only a little bit annoying thing is that it now requires me to have more information, because I need to know the dimension of the subspace, but I also need to know the percentage of corruption. And in fact, you're going to see that in the theorem that comes next, the theorem now will depend on knowing the number of corruptions. But again, theory is theory to just guarantee that things are okay, but often theoretical conditions aren't 100% practical because they depend upon quantities that I can manage.
Why don't we have it on rows? I mean, in addition, so this is completely understandable for columns. So why don't we have it similarly max j max of norm of mu j less than or equal to whole square less than or equal to mu by d, mu small d by upon capital D.
Because
You can have your corrupted entries can be separated out as more towards the right and also towards the bottom. So in the above case, you have done separated out as columns. You can also have cases where it can be at the bottom as well. So both rows and columns are corrupted.
Because of the definition of the problem. The definition of the problem, which I draw here, is I've got data. A fraction of the data, I'm going to call them inliers, and those are points that perfectly belong to the subspace. And a fraction of the data are outside the subspace. Because the way in which the data is defined, which is d by n, and this particular dimension is number of data points, right? What it means is that a column of the data is either in the subspace, and therefore it has no corruption of any kind, or outside the subspace, and therefore it's fully corrupted. So I cannot have a situation where a row is corrupted, because what does it mean to have a corruption of a row? It means that one of the coordinates of every point has been corrupted. In that case, there would be no point that lies in the subspace. Right? So it's more of a matter of just the definition of the problem. You could have defined your data matrix where the points are now rows of matrix, and then the analysis would be entirely the same, but the other way around. So I would have U's over there. So it's a matter of convention.
When you have images which say pixels, which you usually convert into column vectors,
Yes.
in that case you have across the length you can have it randomly distributed. How does it happen?
I'm going to show an example, but what's going to happen in that case is going to be the following. The example I'm going to show in a minute is going to be, I have, say, 100 images, 50 of them are images of faces of the right illumination, our usual thing. The other 50 are random images of anything else. And now I run the algorithm. Can the algorithm automatically determine which ones are faces versus which ones are not faces? And so in that case, the pixel entries are not corrupted. It's just that the whole image is completely different. Okay. Now I have no clue what I was going to say next. Well, the theorem. Right, I stated the conditions under the theorem. Sorry. It's just after 30, you forget things and you don't know where you are anymore. So enjoy your last few years of good memory. Okay, so here's the theorem. So, and this is, I've not been saying, but let me in this particular case, let me quote. So all of these theorems, by the way, are very recent. It's in the last 10 years. So this is 2010. Okay, so it says, if x is equal to L naught plus E naught. So assume that L naught is nu incoherent. With respect to column sparse matrices. Which is the definition we just had. Maybe I didn't say, but is nu incoherent, I should have said here, with respect to column sparse matrices. If just to distinguish from the other notion of nu incoherence, which is just with respect to the set of sparse matrices. So if the matrix L naught is nu incoherent, and and the support of E is less than gamma n. Okay, what that says is if the percentage of outliers is less than or equal to gamma. Then, if the rank of L naught is less than or equal to C1 times 1 minus gamma divided by gamma n. In this particular case, these guys were smarter. They actually figured out what the constant was. Every time the theorems where there exists a constant, this constant is very mysteriously 9/121. Okay? And the lambda, there is a lambda for the algorithm, remember. Okay, the lambda over there, the one that multiplies. The lambda is 3 divided by 7 square root of gamma n. Okay? Then L star is equal to L naught, and P star is equal to P naught. Okay. So again, the theorem is effectively of the same flavor. Effectively it says, if the rank is small enough, if the percentage of outliers is small enough, if the low rank matrix is incoherent with respect to the sparsity pattern that you care about, then this optimization algorithm recovers the exact low rank matrix and the exact sparse matrix that you started with. Something is strange. No. Something is obviously strange. I was just looking at this and saying, this theorem is horrible because the low rank is really low rank as n grows. This is going to be very problematic, and I was just scratching my head, this cannot be right. So, and you should have also said it cannot be. There is also no nu in the entire calculation, so that's a So let's try to understand whether the theorem says what we expect it to say. So let's analyze a little bit the bounds that are in there. This is sort of fairly clear. This just says that the percentage of outliers is less than or equal to gamma. Because n is the total number of columns in the matrix. What does this say? So we would expect, of course, the smaller the gamma, the better things should work. So if gamma is really small, look at what happens. The numerator will converge to C1, and the denominator will go to 0. So it will allow for the rank to be larger and larger. Okay? But obviously, if I now increase the percentage of outliers, right, increasing gamma, what we'd say is that the rank needs to be small. Okay? So in fact, if you plot this quantity, it's probably a curve that is maybe a little bit like that, where this is the norm of E naught divided by n. So this is the gamma, actually. And this is the rank of L naught. So we expect things should work well in this regime. And so I can tolerate a large fraction of outliers, provided that the rank is sufficiently small. Or I can tolerate a matrix with a very large rank, but then the percentage of outliers needs to be small. That's what the theorem says. Okay? Then let's analyze the effect of the incoherence. We've said repeatedly, every time we define incoherence, that if nu is large, things should be harder. If nu is small, things should be easier. So if nu is small, right, the bound in the rank is looser. So I can tolerate larger ranks. And if nu is large, then I'm in trouble again. So it makes sense. Now, how would you, okay, this will take some time to warm up. But now in the So the outlier detection algorithm will be trivial. It's look at every column of E. Those that have non-zero norm, those are the outliers. Okay? In reality, what do you think is going to happen with corruptions with noise? With corruptions with noise, what's going to happen is that everything is going to be non-zero, right? So, but this is what you would expect in practice. You would expect that if you compute the norm of every column, all of these should have small norm, but the outlier should have a much larger norm. So by just putting some threshold on the norm of the columns of E, you will get it right. And in fact, that's exactly what the algorithm will be doing. I'm not discussing the algorithm today, but in all cases, if you remember the algorithm before, we have these shrinkage thresholding operators. What do? For the singular values, they look at the singular values. If they are above a threshold, they keep them and shrink them. If they are below a threshold, they set them to 0. For the sparse part, it was the same. You compare the estimated E with a threshold, and everything below a threshold you set to 0. So once we go to the implementation in the algorithm, what's going to be happening is exactly that. We're going to get the same ADMM with the shrinkage thresholding on the SPD to get L. But to get E is going to be a shrinkage thresholding on the columns of E, as opposed to on every entry of E. So what's going to be happening is exactly this situation, that the E that you compute before the shrinkage and thresholding is going to have non-zero everywhere. But the shrinkage thresholding for E will effectively just put a threshold, and everything below the threshold will be set to 0. So the algorithm will produce exactly that situation, and it comes with a threshold in it already. That comes from the optimization model. So let me just show you exactly an example of that on the data, the example that I was mentioning. Here. Here we go. Okay, so we took a bunch of images from a database called Caltech 101, and here you can see pictures of it. So a bunch of just random pictures gotten from the internet. And we put them together with pictures of faces, okay? And I think if we go to the example here, that's the description. So we take 64 images from a single individual, 64 images in total, and a fraction of them are taken from the Caltech 101 dataset, and the remaining fraction is face images. So what is being plotted here is exactly that norm of the E columns of the E matrix, right? Exactly what I said here. So the x-axis is an index over the 64 examples, so it goes from 0 to 64. And the y-axis is the norm of the columns of the E matrix given by the algorithm. And so in the first example, there is just 5% outliers. And what you can see is that for all of the inliers, the norm is nearly 0. There are just 1, 2, 3, 4, 5 examples for which it wasn't. And the red ones are the last 3 points, in this particular case, are outliers. And you see the norm of the columns of E is much larger. as you put more and more outliers, right, you start to get, these values are higher, but still there is a threshold that is able to perfectly distinguish inliers from outliers. This is now with 20%, and 20% is starting to get tough, right? Okay, but, so up to 20% in this particular case was perfect, but then on, it just continues to degrade gracefully. So now if you put a threshold around here, you will start to make some mistakes, where some outliers are detected as inliers, and vice versa. And so this is now the case with 70%, right? Where you can see that if you put a threshold, you will evidently make mistakes. So the theorem says the algorithm is perfect, provided that the percentage of outliers is small enough and the rank is small enough. So this is sort of just illustrating that that's exactly what the algorithm does. It's perfect in this particular case up to 20% out. All right, thank you guys. See you on Friday.